So you might have heard of recursion before, or seen a recursive function, like this recursive sum function, which returns 0 if the list is empty, and otherwise returns the first element of the list, plus the recursive sum of the rest of the list. But have you ever heard of a recursive data structure? Let's check out a really popular example, the binary tree. We create a class called BinaryTree, which contains one attribute, root of type node, which we initialize to none. We add one function, add, which takes in a number of type integer. If the root of the binary tree already exists, we call .add on the root node of the binary tree. Else, we set the root node equal to a new node, which takes in a number. Let's take a look at the node class with the recursive structure. We define a class node, which has an attribute value, which is an integer, which is also the number that each node stores, which we initialize to none. We then have a left node, which is equal to none, and a right node, which is equal to none. We define the constructor of node to take in an integer, which it then sets to its own value. We then also define a singular function called add. This add function also takes in a number, and if the number is smaller than its own value, then it checks. If the left node or its left child exists, it asks that left child to add the number, and if it doesn't, it creates its left child and sets it to a new node, storing the number. Else, if the number is larger than the value of the current node, we check if the right node exists, and if it does, we say self.right.addNumber. Else, we create the right node by constructing a new node, giving it the number. As you can see, in the class node, we define a left and right, which are both of type node. This is because in a binary tree, each node has a left child and a right child. And depending on if the child is defined, the child carries a value. We can now create a binary tree by setting tree equal to binary tree, and we can add numbers to the tree by calling .add on the tree. When we add 1 to the tree, the root node of the binary tree is equal to none. Thus, we go into the else, and we set the root node equal to a new node given the number. When we call .add 2 on the tree, the root node is no longer equal to none. Thus we go into the if, and we say root node.add the number. This node, which is the root node, then checks if the number is smaller than its own value. Since 2 is larger than 1, it is not smaller than its own value, so we go into the else. Then we check if the right node exists, which it doesn't in this case, so we go into the else again, and we say self.right equals a new node given our 2, or our number. Finally, to add our -1, we call .add on the binary tree, which then calls .add on the root node, and the root node has a value of 1, and -1 is smaller than 1, thus the -1 goes to the left. The left node doesn't exist yet, so once again we call self.left equals new node given a number. We now added 3 numbers to our binary tree, and the structure looks like this. If this video was interesting to you, please leave a like, and if you want to see more content like this, consider subscribing. Let me know in the comments if you're interested in seeing binary search being implemented in this recursive structure. See you in the next one. Bye!